thank you for giving me the opportunity to present my work. So this is work with Jean-Philippe Vert and Andrei Zinoviev. So this talk will be about assessing the prognostic power of mutation profiles. So it's a difficult problem because, as many people pointed out this week, most mutations occur at a very low frequency, and therefore patients share only few mutations in common. So for example, on this lung cancer dataset, most patients share no more than 60 mutations. So that makes the task of predicting survival difficult. So I'll show you an example of survival predictions with Tcga exome sequencing data, so raw binary data. So you have patients times genes binary matrix with survival times for each patient and censoring information so you know whether the patient is deceased or not. And then thanks to this data, you predict survival times. So we model the survival with a linear model of the mutation profiles. And we learn this linear function with ranking support vector machines. And the results we got are the following. So we performed the analysis with 8 different Tcga datasets. And we measured the performance with the Concordance Index. So this index is between 0 and 1. And it gives you the percentage of pairs of patients that were predicted in accordance with the observed survival time. And in accordance means that the predicted and the observed survival time agree on which patient is going to live longer. So as you can see, most cancers have performances between 0.5 and 0.55, knowing that 0.5 is like a random guess. So it's not very good, apart maybe from kidney, which is at 58. Now, if you'd prefer to perform patient stratification and see whether the subgroups have different survival times, well, you would also have some problems because what you hope to have is like some beautiful clusters like this, but what you will get is more like that. You will get one very big cluster where you have almost all patients inside, and a few other clusters with 1 or 2 patients inside. So it's not working either with the raw mutation data. So what we want to do is to integrate the binary mutation profiles with gene networks to derive new representations of mutations, which could yield improved survival predictions and improve cancer stratification. Okay. So there is already some work that has been done about that, and notably the work by Matt and Offrey and co-authors, which Tcga presented this morning. So I'm just going to repeat quickly what they're doing. So the idea is that if 2 mutations have no mutations in common, they can have mutated networks in common. So the idea is to propagate 1 mutation in the network, and in the end, you do this iteratively until it reaches a stationary point. And in the end, every gene has a value between 0 and 1, which represents how far it is from the other mutations. Okay. So you perform network propagation, and then what they did is that they performed quantile normalization after each mutation profile was smoothed over the network. Okay, so we got quite a lot of inspiration from this work, as you will see. But first, we applied this procedure to the binary mutation profiles, and we predicted the survival thanks to that. So NS is network smoothed mutation profile, and NSQN is network smoothed with quantile normalization. And raw is the raw data. So as you can see, well, it works pretty well. You really gain a lot of performance with NSQN, which is good. But what we did is, as you can see, the quantile normalization really improves the results. So we tried to investigate why quantile normalization did really improve the results. So I try to explain this with this little picture. So let's say you have a patient A, it's a binary mutation profile, and you smooth it over the network. So each gene has a value between 0 and 1. And then you sort the mutation profile, and you plot it in increasing order. So it gives you this blue profile. So you see that in patient A, all these genes were mutated, but it's not flat. All mutated genes do not have the same mutation value. And all these genes were non-mutated. And we did the same thing with the patient B, which had more mutations. And what quantile normalization does is that it normalizes all patients to the same distribution. So here it's in light blue. It's overlapped with the red one. And the region which is interesting is this one, where you see that some genes that were mutated in patient B end up with values here that are the same as genes that were not mutated in patient A. And therefore, you can see the QN a little bit like removing mutations from some patients while adding mutations to others. Okay. So next, to understand a little bit better what was happening with NSQN, we perform network propagation, but this time only with one iteration only, and then the quantile normalization step. And what you can see when you do only one iteration is that it does not decrease a lot the results. So it's interesting because it means that when you propagate the mutation of a gene to its neighbors only, well, you do not really degrade the results. Okay. So based on these observations, we designed a very simple method, which we call NetNorm, which integrates also the networks with the mutation profiles. And it's done in 2 steps, a little bit like NSQN, so ranking and normalization. So here the ranking will be made as follows. You rank the mutated genes according to their degree, and you rank the non-mutated genes according to their number of mutated neighbors. And you pay attention that all mutated genes remain ranked higher than non-mutated genes. Okay? And so this is a little bit equivalent to the network smoothing step in the way that it gives a ranking of genes. And then we perform normalization by setting to 1 all the K genes that have the highest mutation value, and to 0 the rest of the genes. So to come back to this picture, it gives us like this kind of stair profile, where each patient ends up with in K mutations. So with this method, we performed again survival predictions. And as you can see, it is quite competitive with NSQN. But it's not so surprising because NetNorm has its own normalization and its own ranking steps as in network smoothing with QN. So then we wanted to assess whether for both NSQN and NetNorm, whether the network really brought something. So we tested the method with random networks. So we randomized the networks by shuffling the genes while keeping the structure unchanged. So here you see the results in green with the real network, and the 10 gray plots are with a randomized version of the network. And as you can see, the performance are better with the real network, and it is significantly better according to a Walsh-T test between the green and the gray plots. So it says that even if we only look at the information contained in the neighbors of a gene, in this information there is something that's biologically important. Okay. Yeah, and to finish, we applied all of these representations to perform patient stratification. So we obtained subgroups of patients, and then we tested whether at least 2 of these subgroups had different survivals with a log-rank test. So this is the log-rank test statistics in the y-axis. And on the x-axis, you see the number of subgroups that we tested. So for the lung cancer dataset, you see, and the one circle means that the log-rank statistics was significant, like under 5%, and 2 circles mean under 1%. So you see that for the lung cancer datasets, net norm gives subgroups which have different survival outcomes. And in the case of melanoma, net norm again gives significant groups, but also an SQN for k equals 4. And for a higher number of subgroups, you see that if you only take the number of mutations as the only information to stratify a patient, you also get subgroups with survivals that are even more different. Okay. So, to finish with, what I wanted to show in this talk is that for survival prediction, using networks really helps having better performances. And there is biological information in the network that's useful. But also that restricting the mutation signal to diffuse only to the neck burst is sufficient to have good accuracy. And that normalizing the mutation profiles is a crucial step to have good performance. Well, thank you for your attention.
Questions?
So the only question I have about the revised method that you presented was, I would be a little worried about the hubness of a node in the network influencing its ranking.
Yeah.
Even if there's no signal there. So the more chances.
Totally. Yeah. Yeah, well, you're right, because it's the case. Hubs are really, you have more, hubs are more mutated in the end than the other genes. But what seems to happen is that the mutational burden in the neck burst of the hub is actually predictive of survival. So you're right about the hubs, yeah.
So for your first point that only doing one iteration of your random walk didn't seem to worsen your results very much, did you find that across a range of restart parameters or just for a more narrow range? So you have a restart parameter for your random walk, right?
Yeah, so...
so it essentially controls the locality of the random walk in a sense, right?
Yeah, so it was performed several times with different values of alpha, which is the parameter that controls how far you go. So yes, it was performed several times.
For larger values, I would expect that you wouldn't see necessarily much of a difference because you're going to stay close to your, you're going to restart very often anyway. But for smaller values, I'd imagine that you would have more.
Yeah, but I don't know if, the random walk happens when you do the whole process of iterating until you reach a stationary point. But what we do when we have only one iteration is just that the neck burr of a genes will receive a certain heat, and there's no random walks anymore. You just receive the heat of your neck burr, and that's the end. I'm not sure if I answered correctly.
Thank you.
So If there are no more questions, thanks all the speakers.